great. Thank you. And so today we're going to speak a little bit about ingesting market data to the cloud and what that means and how we're using Pulsar to do so. So let's talk a little bit about who we are. So Belvedere Trading, we're a small market making firm in Chicago, so around 250 people. And one big thing that we always talk about is our core values, and you can see them listed under our title. But today we're going to be really specifically speaking about innovation, which is a big portion of how we innovate and do things. So we've been around since 2002. We are traders that act as market makers, and we add liquidity to the markets. And so that's generally by putting out a bid and offer into the market. So if you go into your Fidelity or whichever account and you want to trade some option, there's a chance that you might trade against some of our markets. So we trade 2,500 asset classes across 18 exchanges on 2 continents. So a lot of different products, everything from grain products to the S&P 500 to individual stocks and some fixed income. So there's a lot of different types of option classes that we trade. And so to define asset, the way that we define it is it could be trade a stock, we trade a future, we trade an option. And so it's quite a bit of data. And historically, we've been building low latency trading systems. In C++, we have a hardware team that does some custom FPGAs, so a lot of really fast things, which is kind of interesting of what our use cases are to go to the cloud and leverage something like Pulsar. So quickly about me, so I've been here at Belvedere almost 19 years now. I spent about 15 or so of it running technology. Recently in 2016, I guess 4 years ago, moved over to the CEO role and really just working with internal departments on different types of strategies to grow the company in different ways. And so 6 months ago, one of the things that we thought we needed to do was kind of re-look at how we process data and really come up with like an approach to basically take all these different data streams that we have. So chat a little bit about that in the next slide. So the why. So the first thing that whenever we start a project and we think about these things, it's not really about the technology. It's not really about even the people that are going to be there or who are going to be like trying to solve this. It's about why are we even trying to do a certain product, our project. And so there's 3 reasons. There's 3 things that we saw at our company that we thought let's come up with some innovative solutions to deal with. The markets are more related than ever. There's so much more data than there's ever been in the markets. And taking that, but also core, when we're trading in New York, we're trading out in Japan, or trading out in Singapore, or in Chicago, where we're based. Correlating all that data and bringing it together in a way to really kind of understand some of the impacts of decisions that are happening in different geo spaces. It's an interesting question, and trying to figure out like how do we do that in a good scalable way. Also, historically, as we built our application over the many years, we found there's a lot of fragmented point-to-point message streams that kind of exist. And for us to really be able to understand how to take all of this data and then really come up with some very good insights into how well we're trading or what's happening in the market and how can we adjust the way we're trading. That's another big thing that we've seen. And so this is one of the reasons that we formed this team to kind of think about like, what's a different way to approach it than the historic way that we've done it. And then we have a lot of untapped potential. 20-ish years ago when I started in this business, having traders that had like Python and some of these different like scripting abilities was not as much of a skill set. As we're hiring, and we have a pretty big presence of hiring right out of school, everybody seems to have like a computer science minor or some exposure to Python or something, right? So we have a lot of potential on our trading desk to do some interesting scripting, and can we build a platform that takes all of this data across all these different venues and put it together in a way that is usable by these traders, as well as what we call hybrids or quants or even our development teams. So those are the three things that we were looking at. So I'm going to talk a little bit about a what to give kind of a frame of like the type of data that we're talking about. There's been some pretty interesting presentations today and very similar types of topics. One of the things that we have to deal with, and one of my biggest concerns when forming this team was, can we find a system that can handle the microbursts? So if you look at this slide, there's a number up here that says a microburst. And so this is one of the biggest problems that we've had to deal with trading electronically over the many years, is that there are very large microbursts. So the way that we define microburst here is we measure what is the amount of bit rate coming in over 1 millisecond. And then if you took that 1 millisecond, the largest spike of that 1 millisecond, and you said, let's say we sustain that for a full second, what would be our microburst? So if you look at the bottom, if you look under microburst all the way at the bottom, the average bandwidth is 42 megabits per second. Very easy to scale that and take that amount of messaging in to Pulsar, or probably kind of like almost any type of message bus. Then you get into the 1 second peaks, and you say, well, if I took like a 1 second burst of data, and I just said what would that look like over time? That would be 600 megabits. Now you're getting some interesting questions, but it's these microbursts that we see when something happens in the market. You can see this thing go up to 6 gigs, and very rarely do you sustain that. But when the market's crazy, you can see a lot of data coming in. So this is just one of the exchanges that we trade at. And so if you now look at the bottom of this graph, you can see that this is one trading day. We got, what was that, like 750 million packets in that day. The mean message rate was 42 megs. So quite a bit of packet flow. Each of these packets can have anywhere between 1 and 10 messages in it. So we're probably talking about 3.5 to 4 million messages per day from this one exchange that we're seeing, and we're getting these microbursts that we have to be able to churn through and keep up with. And then one other thing that's kind of interesting, if you look at the next thing to the bottom right, there's these top conversations. So it is not actually evenly spaced across these multicast groups, these UDP multicast groups. Some products are just busier than others, and so our top three the top 3 channels from this exchange are a majority of this data, right? And so this is just one of the exchange. As I said, we have 18 exchanges, so we're talking about a lot of data, and we see these huge bursts that we have to be able to churn through pretty quickly. So why Pulsar? So we started this project, and we said, okay, let's look at some message buses. Let's look at Pulsar. We looked at NATS, which is a pretty cool message bus as well, and then and Kafka, right? So we looked at those 3 and said, which one's going to make the most sense for what we wanted. So topics per assets was a big thing for us. We actually, and I'll speak about this a little bit later, we actually had a thought that maybe we could use the topic naming with the regex ability as a schema for finding assets that you're interested in. One thing that we had found, that when we tried to scale up to millions of topics, which I think in the last I caught the end of the last presentation, they were also having some issues with having that many topics. So we actually ended up scaling back some of our topics and then using some keys in different ways. But still, we're going to have thousands, probably hundreds of thousands of topics, just because we trade so many disparate asset classes. And then in those topics, we'll have many different keys based on options and different types of assets that we might trade in those. Multi-tenancy. There's a pretty big regulatory responsibility for us. We have different trading groups that trade similar assets, and we have to ensure that they can't see each other's data. So even though we do not sell any software, we build everything for in-house usage, we still have the need for multi-tenancy and having some good ways to say, yeah, this trading group cannot see the data of this other trading group, and using some of the security features of Pulsar has been great. And then geo-replication. As we said, we haven't actually done this one yet, but one of our things is like, how do we get some of the data that we might have out in Asia and get it to Chicago, get it back to Chicago, and some of these different things. So some of that geo-replication is going to be interesting as we go down that path with Stream Native and Pulsar. All right, so let's talk a little bit about the architecture. So quick plant URL diagram that we came up with. So we have an exchange that's sending us data. So what we do is we have a tap that basically splits the light that comes off the wire. We put it into our collectors. And so what this allows us to do is, given that we have a tap there, plus we use a tap add switch and PTP, so we can get some very, very good timestamps. Like, we have a Grandmaster clock, and some of these are single Grandmaster clocks and things. So we get very, very good timestamps off the exchange boundary. So we can see the data that's coming into our network with high precision of timestamping. So we take take those messages, we put them in these collectors that we wrote. So these are small C++ microservices that, and we'll talk a little bit more about what we did there, but that take the data off that wire, queue it up internally in memory, and then we put it into Pulsar kind of as fast as we can and do a few different things there. So we'll run 2 of those just to ensure that we're not missing data, and do some deduplication. And then we actually send that up into the cloud. So this on-prem is basically our data center that we trade at. Send it up into the Pulsar cluster, and then we actually are using Flink, which I've seen some, at least some chats about other people are using Flink as well. So yeah, there's some pretty cool use cases there of how we're taking some of these data streams, either filtering or joining streams and coming up with some pretty cool insights. And then from there, we're sending some data down into wherever the trader might be, at home, in our office, wherever they are, and showing them some of the data. So yeah, so we're C++. So we, I think that I would imagine that a majority of the people that use Pulsar, are probably Java based and whatnot. So, but we were like, all right, we have a lot of experience with C++. Let's go for that. So, for those of you who haven't done much C++, the modern C++ is pretty awesome. There's a lot of really cool things in C++ 11 and C++ 20 that's coming out, and so we're doing some pretty cool things with adopting a lot of the newest language features. So we actually built from ground up. This team, we actually started with a whole new code base and said, all right, if we were going to redo everything from scratch, like what would we do? There's a lot of conversation about should we use Rust, because it's a pretty awesome language as well, but it seemed like that was going to be a bit too much of change. Other people have spoken about Prometheus and Grafana. It's been great. We've done a very metrics-based approach, and so we have in our collectors Prometheus endpoints that give us a lot of data on how well we can keep up with these microbursts and the data flows that are coming in. And then we use protobuf. I think many probably use Avro, but we're generally more of a protobuf shop. And we use gRPC for other things, and we've done some pretty cool things with allowing some of our systems, when we get to the Theo side, our on-prem systems sending through gRPC gateways into Pulsar, which allows us to have a little bit more control over the data that's coming through, and the ability to modify the data before we put in the Pulsar to a different schema of topics and things. So we've done some pretty cool stuff with that. And then day one quality, I mean, for all of those who are developers, that was one of our mandates. We're like, we are going to ensure that we have high quality, that we understand our system. So use Clang Tidy, we use Catch2. It's a pretty cool unit testing framework for those who are C++ developers. And then we use Sonar, which I would recommend, almost whatever language you are using. So we run around 92% unit test coverage, and we don't have any of the different issues. And so as you can kind of see up in the top right, we have C++, Java, TypeScript, Python, and CSS. So that's kind of the stack that we're using for C++ generally for all the low latency things. Java is the Flink jobs, and then the TypeScript is our UI that is being sent. All right, so this was our first attempt. So if you look at the top graph, we said, all right, let's see if we can keep up with the market data. This is one of those channels. This is one of those really busy channels, and this did not work well at all. You can see that we would run this thing for 15 minutes. If you look at the 240 to 255 window, we run this thing for the 15 minutes, and our queue size internally was 30 million. We were so far behind the market, wasn't even close. And the next things are just kind of a little bit more information. So our architecture was use kernel bypass with a Solarflare card, get the data, go past the kernel, get right into memory, put it onto a queue, and then from there, take it off the queue, right into Pulsar in an efficient manner. And so, that was one of the things. And as you can probably see at the bottom of this, there's a thing where it said we processed 8 million packets. Those 8 million packets ended up being about 60 million. So that was where I was saying each of the packets that comes in, so probably somewhere between 1 and 10. So that's kind of the what we ended up looking at. And so then, as we said, we used quite a bit of metrics-based approach, really trying to understand our latencies and why are we having some of these issues. And so we were basically processing packets. So the top graph here was taking it off the Solarflare kernel bypass, processing it and putting it on the queue. Was probably averaging somewhere between 8 and 3 microseconds, which is obviously too slow. And then taking it off on the other side, and then basically converting it into the Pulsar messages and protobufs and things like that. So the protobuf was actually generated on the first side. So when we took it off the wire, we took the bytes, we map them into protos, put them on the queue, then we build the messages that we're sending into Pulsar, and that took basically somewhere around 13 to 21 mics. And so this is where you could see, right? So if you're generally taking on one side 8 to 13, and then on the other side, 13 to 21, you're just going to keep falling behind. So what did we do? We kind of dug deep into Pulsar configs, spoke a lot with Stream Native. We talked to Matteo, we talked to Addison quite a bit, CJ. They were all very, very helpful. Learned a lot about how the blocking works, which was kind of interesting. We didn't really realize that once you hit the block, so we're doing asynchronous messages, but once you hit the block, it would stop, right? And then at that point, it would try to send all of the data out, and then it'd come back around. So we found some things there where we could adjust some of our size of our configs. We tried partitions, which we thought was a pretty good concept. The thing was that when you're taking the data off, we weren't queuing much faster than where you could leverage multiple partitions on the C++ side. So what we actually ended up doing is we found a good way to partition the multicast groups. So we took those, and then those multicast groups, and we could run multiple microservices that took that same one big multicast group and broke it down into smaller ones. So we got a lot more basically sharding of the data. Learned a lot more about the batching, got into kind of how it works, read through a lot of the C++ code, and really started understanding how we could optimize batching for our use cases. For those who've done C++, there's a lot of compiler optimizations that can be done. So we did those. We moved from a regular queue to a lockless queue. So we found a pretty cool open source lockless queue that we used that was very efficient. So that definitely helped. And then we actually, Protobuf and also Pulsar on the C++ side have a zero copy functionality that allows you to not have copies happen. So we moved to a fully zero copy between the protobuf into the byte array all the way through into the Pulsar parts, and we zero copied all the way through. And so that definitely helped in terms of the helping our performance. So what does this look like? So this is the same channel. We got our processing latency coming off the wire in the protobufs and into the queue to, let's say, maybe 3 to 5 microseconds. On the other side, putting it into Pulsar, we got that also to about, I don't know, it's about 3 to 5 microseconds as well. And then we also sharded out so that we had multiple, basically, ingesters for the bigger channels, and then maybe just one ingester for some of the smaller channels. And then you can see like our queue size, at some points we hit up 50K of these messages and come right back down. And we were basically going through, I think this was running through one of our closes at 245 to 315, and we were able to ingest 40 million messages. We would say that's a pretty good win. So this is just one of those channels. This is not if you think about that first slide where I said, hey, look, this is all the data. So this was just in this scenario, the 311 channel. But then we did run it with all of the channels and everything worked pretty well. I don't think I have a slide on that. Cool. All right, so this is pretty cool. But first of all, you're a trading firm, and some of these might be questions that you're thinking. It's like, well, you're a trading firm and not a market data vendor. Like, why are you doing this? And how does this actually get you to that why of the things that we said before? And maybe you're also thinking that I can't believe you write C++ code. So the next piece of this puzzle was the market data is pretty interesting, right? So yeah, you kind of have to know what's going on in the market, but that doesn't really give you all that information. So the next thing we did was we took our theoretical models that we are generating in real time on our on-prem system, and we uploaded those into the cloud, into Pulsar as well. And what this allows us to do, and this is where that Flink job comes in, is it allows us to take market events that are happening, our theoretical values that are happening in real time, and join those streams to give you some pretty good insights into what's going on. So we adjusted all of our theos, did some correlations between market ticks and valuation. That's some pretty cool things that we're starting to put together with this. And then because we were starting from scratch, we also had this thought of we need to come up with an extensible framework to add many more of these data streams into our into Pulsar to correlate more data. There's a lot more data on-prem that's not Pulsar. So we created an extensible framework to do this. So this is what our theos look like. So we ended up having 10 ingestors that are running up in the cloud. Our Theo engines are sending gRPC. I think let's say we have 100-ish Theo engines that are running on-prem. They are sending over gRPC through a load balancer into 10 different pods. I guess your replicas, depending on which way you want to talk about it. And then each of these pods is responsible for taking that message, converting it into a format of like how we want to think about it, and then sending it into Pulsar. Now, one of the things that you can see here, which is kind of interesting, is that you see that, let's say here at 6:14, around 8 a.m., there's a green line that just drops, right? So that was us restarting. And what we were finding was that because we were creating we were actually creating like, I can't remember what we ended up having. We had like, I don't think we had 1 million topics yet, but maybe like 500,000 topics that we like spun up. That was causing a lot of issues in Pulsar. So then, just recently, I think yesterday or over the weekend or something, we redid some of the way that we're creating topics and things. So now we're keeping up much better. We're still seeing some things where we need to add a little bit more scale to the Pulsar cluster, so it doesn't it doesn't back up as much. So there's a lot more information that we're still learning about this, but we were able to successfully get all of our Theos in there. And even on restart, it just kind of restarted and everything started flowing through again. So it's pretty good. All right, so Flink. So Flink is basically the way that we're thinking about using Flink is we're gonna have some long running jobs. Those things are going to be things that we feel are data sets that provide a lot of value to many end users. We're gonna create them. We're gonna host them on the back end as part of like the data engineering and data science team. Run these things all the time. They're always on. They're creating data sets that we feel are very valuable. Then we're gonna have some ephemeral Flink jobs. That's gonna be like the next way we're doing. So we're gonna build some jars that do specific things, but we want users the ability to turn them on and off with different parameter sets. So that's kind of part of one of our GUIs that we built. We're having the ability to create the parameter set and upload a jar, start it, and all that stuff, and then send that data into either a temporary topic that might not be persistent, or maybe a persistent topic if we decide that it's useful for us to keep it. And that will be probably a majority of our jobs will be something like that, where we create custom jobs that have a set of like inputs that do certain functionality for our end users. And then they give the answers over a stream. And so to our front end, we're using the WebSockets, which is pretty cool that you can do a WebSocket from Pulsar directly into a website. So basically running a job, taking a bunch of data, compiling it down into something that's useful, setting over a WebSocket and having it show up in a website. Something like that is our general use case. And then the part that that one of our whys was like, hey, we have a lot of people that have some interesting scripting abilities. So allowing the ability for people to write, integrating that into Jupyter notebooks, running some of these jobs more ad hoc for custom computations. And we're still kind of working through getting that to work the way that we want. So the first two are a little bit more first-class citizens of our system, and the third one is something we're going to be working about with, like the Flink SQL gateway, the Pulsar Flink connector, and so here's one of the jobs. So this was actually one of the jobs that was looking at that data stream that was that 311 data stream. And what this was doing was taking every asset that was coming off, or every basically order and trade and everything that's coming off, and we ran like a simple calculation with a tumbling window and aggregated some of this flow by asset and sent it back out and said, all right, this is some information about what happened over the last 100 milliseconds or second, or I don't remember which one this was configured, but and show that on a user interface in a way that is useful to some end users. That's been pretty cool to get some of those things to work. And then last, so future. So there's a few different things that we want to do. We want to work on capturing more types of data. One of the big ones is right now we're doing the market data in our theoreticals. So getting all of our order flow and quote flow that goes out to the market and correlating that with what's happening in the market, what's happening with VOs and those things. Really get that geo-replication working, and maybe even look into a hybrid cloud Pulsar, since we have a data center. We have a few data centers that we have on site across the globe. Does it make sense to have a Pulsar there for some reason? So these are the things that we'll be thinking about as we really start pushing the Pulsar system with all 18 exchanges and some of the different use cases. Next one, expand to all those exchanges and start getting all that data in there and start running correlations and things like that. And then we also have another 100+ internal proprietary data streams that we find that are useful, that not nearly the same capacity of data. So we started with the biggest ones. We took the ones that we thought were going to be the hardest to get into a message bus. Everything else after that becomes smaller in scale, except for the exchanges. Those are can be very similar, but there's the proprietary ones are probably going to be smaller. So we feel that those will be more of a layup as we sort out all these scale questions. And then scale our Flink job offering. I think that's going to be a big part of how we can empower end users to run custom analysis, either through a precompiled jar or through Flink SQL. Last